inviting me to give this talk. And good afternoon, everyone. My name is Mahesh Morjaria. I've been with First Solar about 7 years. And prior to that, I was working for GE for about 20 years. I have been in renewable fields for quite some time. And I'm looking forward to sharing with you some of our experiences on utility scale PV plants. The key message is, and feel free to stop me if you have any questions as well. We will certainly leave some time for questioning at the end, but if you have something that's urgent, by all means. So the key messages I want to leave you with is that the utility scale solar electricity now costs less than conventional generation in many markets. It is less expensive than rooftop PV, by the way. I mean, rooftop PV is widely used, but generally that tends to be more expensive because of scale of the utility scale and so on, utility scale power plants, that is. Now, what I'm going to share with you is how did this come about? What were some of the cost reduction drivers? And they included certainly the module cost reduction and efficiency improvement. I work for First Solar. First Solar is a module manufacturer, and we played an important role in reducing the cost of the modules. But most of my talk will be focused on the power plant level. That's really my expertise as such. So the cost reduction have also included BOS, or balance of system, and plant design innovations, and I will share that with you as well. Excuse me. So one other improvement has been just the investment climate, and what I mean by that is that PV plants in general are very capital intensive, and most of the cost is associated with financing the plants. And so with the more acceptance of those plants, the climate has improved, and hence their cost has also reduced. Now, if you go forward, what are some of the challenges that we're going to face? Cost was certainly the first challenge that when we started off, maybe about 7 to 10 years back, where grid parity was the biggest discussion. Now the next discussion is more about how much can the grid actually accept solar, and that's what I will talk about as well. So the challenge is how do you maintain grid stability and reliability while integrating large amount of large-scale solar into electricity grid system. And particularly the driver is to increase grid flexibility so that we can increase the solar penetration and reduce curtailment of solar as such. So with that in mind, let me share with you some of the data that many of you may have already seen, but nonetheless it will be important to keep it in mind. So here is a chart which kind of shows the levelized cost of energy. This is from the Lazard version 10.0. And if you look at that, on the y-axis is the levelized cost of energy as measured in dollars per kilowatt hour. The coal goes anywhere from somewhere in 5 cents to 15 cent kind of range, etc. And you can see pretty quickly that in U.S. especially, that the gas combined cycle is one of the cheapest the cost of electricity, and that's why it has had a tremendous increase compared to, for example, coal, and nuclear is up there as well. Gas peaking and diesel are quite expensive. Whereas solar, and I'm talking more about unsubsidized solar, is in the range of about 5 cents per kilowatt hour. And just to give you some headline numbers, in April 16, Mexico had an open auction and asked for prices from the marketplace and got solar at about 5.1 cents per kilowatt hour. And then in September, they had a similar auction, again, the next version, about several hundred megawatts, and they got it at 3.4 cents. And then again in October, so just a month later, they had another auction, and in that case, they got it at 2.7 cents. The bottom line is that these are the kinds of prices that are seen elsewhere. So for example, in Abu Dhabi, the price went down to 2.42 cents in Abu Dhabi. This is in 16 now. Recently in 17, Tucson Electric, they were in May of 2017, they're getting prices of about 3 cents per kilowatt hour. And these are 20-year contracts, so this is a fixed price for a pretty long period as well. And then recently in Masdar, this is in also in United Arab Emirates. I'm sorry, this is in Saudi Arabia. This is the price of about 1.79 cents per kilowatt hour. And actually, you guys are right there in the area in Austin, Texas. The latest one just last month, December 20th, the price was 2.5 cents per kilowatt hour. So these prices are quite real. This is happening, and it has happened quite rapidly as well. Now, if you wanted to look at the data from globally, this is the charts which kind of show on the y-axis the prices in dollars per, in this case it's dollars per megawatt hour, and the circles represent the size of the plant, and this is all over the place, whether it's in Asia, North America, Latin America, etc. And you can see that there is an inexorable trend towards, if you draw that line, it's about 5 cents or below that as well. Why has that prices dropped? So the first thing is that the module cost has come down quite a lot, and if you look at this experience curve for the module, on the y-axis is the module average selling price in $25 to $2015 per watt, and in 76 it was close to, and this is a logarithmic scale, in the range of high 80s, 90s, and now it's the volume has shifted, volume has increased, and the prices have dropped quite a lot. So in 2016, the price we ended up with about 35 cents per watt, and a volume of about 310 gigawatts. So quite an achievement, and you can see that the trend is continuing on as well. And we should be about, volume-wise, about 3 terawatts of deployment by end of 2030. I think we are about 300 plus right now. Now, it's not just the module cost that has come down, but even the balance of system costs have come down. So if you look at this particular chart, which is now looking at the system cost, which is the utility scale system in terms of dollar per watt, the Sunshot mission wanted to get that below $1 per watt by 2020, and as you may have often read that already dollar per watt has been achieved by last year, in fact. So this is quite an achievement, and so we have had a significant impact from the balance of system and other costs associated with the plant as well. So let me then talk about the utility scale PV plant and some of the things, some of the innovations that have made this possible. So here is a picture of a typical utility scale PV plant. This particular one is in Arizona. It's a 290 megawatt plant called Agua Caliente, and I just picked up to show some of its features. So when you look at a plant like that, it is dominated by the array of PV panels, which is kind of shown there. And then that small white dot that you can see is a power conversion station, which converts the DC power into AC power. And then finally on the bottom right here is the substation that aggregates all that power and sends it into the transmission grid. John, I'm assuming you can hear me all right? Yes, I guess so. Okay.
Sorry, yep, we can hear you perfectly.
Okay, terrific. So in a typical PV plant schematic, we have, for example, start off with the modules, which convert sunlight into DC power. We organize it in terms of solar arrays and use combiner boxes to aggregate the DC power. And the typical voltage, DC voltage that we work with nowadays is 1500 volt. It used to be quite common to do 1000 volt, and previously it was more like 600 volt DC. So that's the voltage level we deal with. And then there is a power conversion station that converts the DC power into AC power and steps it up. Typical AC collection voltage is about 34.5 kV AC. This is also used in the wind plants, and that's the reason that this particular voltage level is adopted. Then that all power is aggregated further in, and we have switch gears that we use and feed that power into substation that will step it up to anywhere from 69 to 765 kV AC. So that's a typical schematic of a PV plant, and what you have is essentially more of the same. One of the nice things about the PV plants is that the technology is relatively simple. There are really no moving parts per se, and it's just a large number of same equipment all over. So we may have millions of these modules and hundreds of these power conversion stations, etc. But otherwise, the technology is just the same as well. Typically, we refer to balance of systems as everything but the PV modules or PV panels. So we divide the cost typically with the PV modules and then rest of it, the balance of system. And specifically, we define this DC balance of system. This is the DC field all the way to the inverter level. And it's all dependent upon the efficiency of the modules itself as to how big that would be, etc. And then rest of it is fixed or AC BOS. The reason we think of it as a fixed is if you are a 100 megawatt plant, then the BOS portion that is referring to the AC portion of that is generally well established, whereas we can increase the number of modules and so on to increase the DC size, and I'll show you why that is important. Now, one of the first things that I remember when I joined First Solar about 7 years back, that was probably the last time that we designed plants at 900 volt DC, 600 volt DC. This is a typical NEC, in-home kind of a residential DC collection system. And the plants were all designed at 1000 volt. Why 1000 volt? Well, the higher the voltage you go, you can build it into, you have less losses, you can build into larger plants, etc. And so we started building, instead of 1000 volt to 1500 volt DC, and developed at that time, this was almost 4 or 5 years back, with GE, a very large inverter. This is a 4 MVA inverter at 1500 volt DC. And usually I ask people to look at this kind of two arrays. One is a 1000 volt DC on the left. The one on the right is a 1500 volt DC, which has the same amount of PV arrays in terms of PV modules and so on. And which one do you think would have less cost? And I think most people would look at that and say, obviously the one on the right has lower cost because A, the number of power conversion stations is fewer, the roads are fewer, it's a simpler design, etc. And that's indeed the case. So we were able to move from 1000 volt to 1500 volt, adopt bigger inverters and make it much more cost effective. So the savings come from larger, more cost effective inverters, actually, because we have fewer power conversion stations, you have fewer connections, you have fewer of lots of things, and that reduces the cost as well. And it also has an impact on the DC and AC wiring. You have less of AC wiring. DC wiring is certainly longer, but it has a higher voltage. The losses are reduced and so on. So that's the one example of an advancement that we have carried out, which now is common in the industry, by the way. In fact, we pioneered this particular approach for solar, and since then, almost all the utility scale players have moved towards 1500 volt design, and so has the supply chain as well. So then usually the question comes back as, hey, if going from 1 kV to 1.5 is good, why wouldn't you just continue on? And I'll give you an example of that as well. And by the way, savings also come from, in this case, the O&M savings, because you have fewer number of power conversion stations to manage. Recently, there is a development of string inverters. So if you look at in the past, the string inverters, we would have hardly considered string inverters as being viable for large utility scale PV plants, especially if you look at this particular chart, which shows on the y-axis the cost per watt AC of string inverters, which is in the black there, and in the blue is the central inverter. The central inverter costs were always lower, and but recently the companies like Huawei and others have increased the volume of string inverters and have managed to bring down the cost by scale, by just the manufacturing scale. And the question becomes, hey, is that a viable alternative to reduce cost? And we've been exploring that. So from the previous architecture where we had the arrays and then we had the combiner boxes, and then we take all that DC power and aggregate that into the inverter, that's the central inverter architecture that I kind of showed you before. One can imagine instead of the combiner boxes, we would put string inverters and basically get a different architecture where the conversion between DC and AC occurs more closer to the arrays themselves, as you can see on the picture at the bottom or the schematic at the bottom, and then you may have a centralized transformer. Again, the transformer cost is the driver here, and have a similar architecture. So this is being explored by us. I mean, I think there is a room for reducing the cost further by adopting string inverters. And the cost savings comes from having no combiner boxes, for example, and improved O&M, and the idea being that if there's any problem with the inverters, we can just replace the string inverter. So then the question that I ask myself is that another way of doing this particular architecture, and these are all related to the balance of system. We can get rid of the combiner box and even the inverter and the PVCS by essentially instead having a medium voltage DC architecture where we basically use a DC-DC converter that steps up the voltage to a much higher level voltage, maybe anywhere from 5 kilowatt DC all the way to 20 kilowatt DC, then can be put into a very large inverter. And there is a very well-established industry for large inverters from the tie lines. These are the ways by which you convert AC from one synchronous network to DC, and then DC back to another synchronous network is the tie line between like Texas and Mexico, for example, that you can use that technology. So we had just to wrap that up, we had actually started working on this particular architecture, but now for a variety of reasons we are not pursuing that, but many of the research organizations, etc., are actually providing proposals to Sunshot Department of Energy, the solar technology to develop this kind of an approach further. Anyway, so it gives you an idea of why we do, what kinds of things we have done in order to reduce the cost of solar. One other factor that comes into play is the design of the plants themselves, and so I'll give you another example. Here you can see for the same plant, depending upon the irradiance day, if it's a high irradiance like in middle of summer versus low irradiance maybe in the case of winter, the power that you will produce from the same plant will be different. So how do you design this in a way that actually optimizes the output of the plant over the whole year? So the way we do that is by, if you think about it, we can increase the DC power capacity. For the same amount of AC, if we keep increasing the DC power, it will kind of act like it is increasing the irradiance, or for the same irradiance, it's increasing the power, as kind of schematically shown here. However, we have a power conversion station that has a limit on a particular AC power. So as you can see on the top figure there, at some point the AC power limit is reached, and if you keep adding more DC power, you're going to hit into the clipping losses, which means that that energy that kind of represents in the dark blue there is energy that's not captured by the system itself. So how do you decide where you stop? I mean, so the way we kind of figure that out is we look at the levelized cost of energy and what is the optimal range at which we would have the DC design. So in particularly, we look at the levelized cost of energy, which kind of shows by this the graph A, which shows that as you increase the DC-AC ratio, it actually continues to go down because you are capturing more energy, even if there is some clipping going on overall through the year, and so your cost of energy will go down for a while, and then it will start increasing as you add more DC, because now you have a lot more clipping losses. Another way of looking at it is NPV, net present value, for a whole project, in which case you're looking at the return on investment, which is NPV is another proxy for that, and that will maximize even beyond the LCOE, because you're still gaining some revenue from certain power purchase agreement, etc. And so you might have an optimal location, optimal design point somewhere further right. So these are some of the things that you have to pay attention to, especially on the utility scale plants, to ensure that you get the maximum value out of the plants as well, or in this case, depending upon the criteria that. Now, one other advancement that we have done, and this is specifically to First Solar, is that we used to have a Series 4, which was the form factor of that was about 0.6 meters by 1.2 meter, and instead now we are making it into a much bigger module. It's 3 times as big, and using the same manufacturing process. So by making it, it's like I often describe it as we used to make a 6-inch pizza, and now we're going to make it into 18-inch pizza. Same recipe, same everything, except we need a bigger oven that happens to just cost $1 billion. But other than that, it's the same idea. And so this bigger module of this kind would further reduce the cost. And in this particular case, when we compare to, for example, silicon modules, which are 1 meter by 2 meter high, this is a little bit larger format. It can be installed much more, at about the same rate as the silicon module, but you will install a lot more watts per labor hour and so on. So it's a new product that will actually further reduce the balance of system cost. Bottom line on all these ideas that I mentioned are things that we have used in order to reduce cost of solar. So in particularly, if you look at the cost of solar, the module cost in 2019, for example, represents about 1/3 of the cost. The balance of system, inverter, electrical BOS, system BOS, labor, etc., represents another third, and so on. So we are continuing to drive all those elements down in order to decrease cost. Now, if you have decreased cost and the cost of energy is so cheap, what stops us from basically blanketing the whole planet with solar and just generating electricity from that? Well, the amount of electricity that solar electricity that can be absorbed into the grid is a concern. So what I want to talk about next is some of the issues that we reached in terms of grid stability and reliability. And you can think of it in three different categories. One is grid stability from a very short-term perspective. You know, are you having the voltage and frequency in check within the normal bounds? If not, then you have a problem. The second element is about load balancing. You know, in a 24 hours day, do you have enough generation to meet the loads, and how are you balancing that two things? And the third thing is about power systems planning and design. How much solar will we have 20 years from, 5 years from now, 10 years from now, 20 years from now, and how would that all work out in a planning systems perspective? So I'm not going to go into a lot of those details, but the focus will be more or less on the first category, where we're talking about, you know, maintaining the voltage in the normal range and the frequency, which is a proxy for ensuring that the generator power equals to the loads, or any loads plus any losses at every instance. So how do we manage that, especially if you look at a typical PV plant output, which can vary, like kind of shown here, where the red line is actually the irradiance and the green line is the power output of the plant. So we take the power plant, and on top of that we have layered a power plant controller with a SCADA system, and this power plant controller monitors the grid conditions and ensures that it commands the inverters. Inverters are the active elements in that, and there could be hundreds of these inverters, and sends them commands so that the whole system works as a one harmonious unit. It's almost like an orchestra conductor, where the controller is ensuring that the total output of the plant is what we desire to be. And this is a closed loop system. It's about running at 100 milliseconds, so pretty fast, so it can actually take care of lots of things as well. So here is you know, fun data that we have collected. This is 20 minutes passage of clouds going through that plant that I was showing you a picture of, 290 megawatt plant. And one of the things you can see from this one is by managing the whole plant as a collection, we are pretty much maintaining the total output of the plant to be relatively stable, as kind of shown on the right side. And yeah, so, and of course large plants are attenuate the impacts of cloud passages. But if you have many plants as well, the clouds are really not as big an impact as would be the case if you didn't have a lot of geographical arrangements as well. Now, I wanted to share one other thing, that when we are building this particular plant, Agua Caliente, which is on a 500 kilovolt transmission line, and worked with the transmission operators, and asked them, hey, we are building this new plant. This was in this is into 2010 timeframe. What are the kinds of features that you would like the plant to be? Do you want us to control voltage and things like that? And the transmission operator said, hey, look at that particular plant at the end of its Palo Verde nuclear generating station. It's a 3.6 gigawatt of a plant. And even though this 290 megawatt was the largest plant at that time, PV plant in the world, Hey, you are still a small potato and we don't think you can do much about the voltage, so you just stay at a constant power factor and, just don't bother us kind of a mindset. And operate at unity power factor. So this is typically how the plant operates, where the power of the plant comes down. This is a nice clean day, and you can see the power going up in the middle of the day, and then it is limited because there's a transmission constraint or the plant level constraint, and we maintain that. There is some reactive power produced in the plant, which we manage in order to get a constant power factor. See the power factor line is at 1.0 and it remains constant. And the voltage is maintained pretty much by the nuclear power station, so we don't maintain the voltage. So this is how the plant runs quite well, as you can see. Well, 3 years later, after the plant was commissioned, this particular transmission line went out of service, and the grid operator started noticing, see that black line? That's where remember previously the voltage was very stable. Here the voltage is fluctuating because that nuclear plant is no longer on that network. And so the grid operator said, hey, you guys were saying something about grid-friendly power plants. Can you see if you can control the voltage? And so you can see that black line, which is the voltage, it is being controlled, even though the power, which is the blue line, is changing. So the most important thing I'm saying is that we built in the ability to control the voltage, and we are able to show that this is actually doing that. And at night shutdowns, at nighttime, of course, the plant goes down and the voltage starts fluctuating again. But power electronics can be used to even control voltage at nighttime. Anyway, the bottom line is we build all these plants with this kind of capabilities of voltage regulation, real power control, etc. And these are all the grid-friendly features that are required by NERC for a plant. And so indeed the utility scale plants, unlike rooftop PV or some other PV plants, they do contribute to grid stability and reliability like conventional generation. That's the bottom line. Recently we had a question about essential reliability services. We ran a demonstration with the CAISO and NREL on a 300 megawatt solar plant. And the question was, can a PV plant provide reliability services? And particularly, NERC has identified frequency control, voltage control, and ramping capability or flexible capacity as being the necessity for providing reliability services. And certainly I'll show you the test results of some of the test results. And indeed, those plants can provide those capabilities. Not only that, but it actually can do a very good job of that. Now I'm running out of time, so I'm running it a bit fast. So let me just say we took this 300 megawatt plant and ran them through this kind of service. And particularly, we took a service called AGC, or Automated Generation Control, where if you look at this plant, the available megawatt, this is in the morning, the plant's available megawatt is increasing. This is from in the morning time frame. And we took provided it a 30 megawatt headroom and used that headroom to get a signal from the grid operator. This is a 4-second AGC signal, and that was provided to the plant controller that I described before. And this, you can see the measured megawatt. This was the actual data from the plant is shown there. And over the period, the measured megawatt pretty much mirrors the signal that we got from the grid operator. So every 4 seconds, you're getting a new set point, and we are following that set point. Same thing, we did it in the afternoon as well, and pretty much you can see the results of that are really good as well. In fact, you should ask how good are the results. So here is the accuracy of frequency regulation from CAISO from various different generation devices. So from an example from steam turbine, it goes, the accuracy is 40% accurate, which means it can follow that signal 40% of the time. Think of it that way. And gas turbines, which are really fast, can do about a 63% level of accuracy, whereas the PV plants, the regulation accuracy is about 24 to 30 points better than fast gas turbines. Now, there is no magic here. This is really power electronics that is able to follow that quite well. So not only the PV plants can provide reliability services, they can actually outperform conventional generation in that regard. So that was the main result. If you guys are interested, there is a report that's been published. You can read that up, and you will see that the main message being that indeed you can use renewable plants, or in this case PV plants, utility scale PV plants, to provide that services as well. So, and the reason this is important is that means that you don't necessarily have to have conventional plants running around just for reliability services. That's the main message. When a PV plant is operating, you can use it also to do other things that is essential for that as well. With that, let me continue on. One of the concerns is about, okay, there is too much solar, and many of you may have probably heard about this duct chart. And what the duct chart represents is two things: that if you look at as solar penetration goes up in the middle of the day, they expected and this is by different years, in 2020, the belly of the curve to become deeper, and that means that you have this concern about how are you supporting the net load where you have many must-run generation resources. And so actually, instead of 2020, net load has already been lower than that, 8.5 gigawatt in 2017. So this is already happening. So that, and the other concern is the high ramp rate in the evening, because in the evening time, now the solar goes away and you need the flexibility from other generations to ramp up. And that is expected to be about 13 gigawatts in 3 hours. And already in December of 2016, they sold the 13 gigawatt ramp. So then the question says, hey, if you're looking at this kind of a diagrams, then isn't solar already causing a problem? And in reality, this is not a reliability issue as such. And so if you look at the generation resources behind that duct curve, this is from May 14th of 2017. This is what it looks like. So you have a whole bunch of, there's a nuclear at the bottom, which is the base load, the imports coming from other side system, thermal load. This is all California, by the way, hydro, solar, and then there is some level of curtailment occurring of solar because there is just too much solar at that time, and the minimum must-run generation of 8.5 gigawatts cannot be pushed down any further. And then there is the behind-the-meter solar. So this might give you the impression that, hey, we can't add more solar, but what I wanted to share with you is that if you look at that same system, but now look at the data from August 29, 2017. This is summertime now. Now, if you look at the diagram on the left where the electricity is much more valuable, you can quickly see that there can be opportunity to add more solar to that by all means, because if solar will be cheaper than all that thermal and imports, for example, and it will satisfy the GHG goals, etc. So there is no reason to think that solar is saturated. In fact, where solar generation has higher value, there is opportunity to add a lot more solar. California right now is about 9% penetration of solar in their overall energy mix, and the opportunity is even higher to do that. Of course, now if we added more solar, like kind of shown on the left-hand side here, by pushing the thermal and imports lower, it will end up with a lot more curtailment of solar in the low load day. But that is all about the economics. And so if we can add flexible and controllable solar, we can drive the economics of this situation and optimize what makes sense for the overall system. That's the main message. And I hope that came across. Anyway, so the way we are thinking about solar going forward is that solar 1.0 is like the traditional solar where the load, the solar amount is low, and it's only the energy only value. And with that, the net load shape, which is solar load minus solar, is what is dispatched in a regular power system. The next version of that would be what we would call solar as dispatchable solar, in the way that I explained before about reliability services and flexibility, by adding plant controls and enable additional grid integration. So here the solar proportion has gone up, as you can see here, and then it gives rise to a net load shape, which is like the duck chart that I was showing you before. But by curtailing solar or targeting a certain amount of solar to be curtailed, we can shape the net load profile to suit the need of the system as such. And then finally, solar 3.0 would be the case where storage starts getting to become much more cost effective, and it can add a firm generation capacity value so that we can add even more solar and transfer some of the energy into storage and essentially end up with a much smoother net load minus solar minus storage, as kind of shown here. Anyway, this kind of gives you the idea of how we are looking at solar in general, and as we grow solar from 1.5% in U.S. that is today to anywhere like a DOE Sunshot program has up to 55% of electricity coming from solar by mid-century. So this is part of our game plan to help make that happen. With that, I want to summarize my message. Essentially, it's showing that utility scale solar is now costing less than conventional generation in many markets. It is cheaper than rooftop PV by a factor of 2 to 3. There is probably opportunity to reduce the residential rooftop PV cost quite a bit. But the key cost reduction drivers have been module cost reduction and efficiency improvement. This is what I showed you as well, the BOS and plant design optimization as well. And finally, the thing that we need to work on is addressing the grid challenges of how to accommodate more solar, because it is low cost now, because it is the first choice in many markets, and while maintaining the grid stability and reliability, and so on. With that, I think I'm going to go open up for any questions that you may have, and so on. I see, John, there are a whole bunch of questions that came up as well. And yes, the slide deck will be provided, and I sent it to you as well. And we'll record the talk, and okay.
Okay, so it looks like you must be seeing the chat window yourself then, or would you like me to read any of the questions to you?
I'm seeing the chat window. So one question is, in recent trip to India, I heard some discussion of loss of power if panels get covered with dust or grime. In desert conditions, access to water to clean panels might be a problem. If there is water, solar could compete with agriculture. I imagine that compressed air could be used, but do you see cleaning panels to be much of a problem? Okay. So yes, there is certain loss associated with soiling of panels in general. So generally what happens is that in many places, especially in Southwest U.S., for example, there is no cleaning of panels. People just wait until it rains and it clears up. But we have systems in other locations where we measure the amount of soiling. The way to measure that is really simple. We take one solar panel which is cleaned automatically and another panel which is just exposed to the normal conditions. And when you see the power difference between the two sufficient to take cleaning actions, then people will just go over the panels and can do either dry brush, which was the question about that Joshua asked about availability of water. So in cases like Abu Dhabi and Dubai and all that, water is not widely available. So they just use the dry brush to clear out sand or things like that on a somewhat regular basis, depending upon how much it has accumulated. But other means of like compressed air can be used, but I think it is actually, I'm not sure if it has been widely, I don't think I've seen many places where compressed air as such has been used, because dry brush seems to be working fine, and most of our panels are, at least the first solar panels, are glass panels, and they are just like the windshield on our cars, and so it's not as big an issue per se. Second question that Josh asked was, he would love to hear thoughts on the implication of tariffs that may be imposed at the end of January or on some kind of solar panel imports. Okay, so this is the import case, trade case that is occurring right now, the case being brought by Suniva and Solar World, and particularly asking for trade relief, or rather a tariff on imported panels, especially from China and other places which have had a negative impact on their economic viability. In general, there's a lot more capacity has been built in many countries than supported by the demand, and that has often caused the price of panels to be reduced quite a lot. But we think that, and that has had an impact even on companies like First Solar. We had to actually abandon certain lines of products and go to invest a significant amount of money to reduce our costs further. So there is some level of justification for that trade case. The question then becomes, what's the particular remedy? And so we are not necessarily advocating a high level of tariffs as such, because then it impacts the overall solar growth in this country. But some kind of relief may be appropriate. But nonetheless, it's now up to President Trump to decide on that particular case. But if there is a big tariff increase, then what it will do, it will increase the cost of solar in the U.S., not anywhere else, and it might then slow down the growth of solar energy in the U.S. But we'll see. I don't know what else to say. Is First Solar considering DC coupled storage to capture the clipping losses? This was a question from Peter, and Peter, generally we evaluate that, but let me give you an idea about some of the thought process. Is that uh, using storage to capture energy that would otherwise be lost is always would seem like always a good idea, but the question is what's the economics? So if, for example, if I were to add, let's say, 10 cents for every kilowatt hour of energy that I capture into the storage just as an additional cost of storage, would that make sense? Well, in some cases it doesn't make sense. If the cost of energy is 3 cents and I let's say clip 10% of that, and that's I'm losing 3 cents of energy, and then I add 10 more cents to it to store it, and then if I don't get 13 cents back from the grid, then it's probably no point. It's almost like losing money on that purpose. So it's not very simple. And then if you have to have a DC coupled storage, it has to be distributed on the DC side of the inverter. So complications like that happen, and it's not a straightforward consideration. It can be done technically, but practically, no. Today, anyway, the cost of storage is high enough today that it doesn't make sense. The second, I hope, Peter, that you can send me your question again if you feel that, if you have more thoughts on that. Dave had a question, is there an optimal area size per MPPT that significantly affects overall cost, LCOE, and PV? In general, for large utility scale plants, we haven't seen that much impact of string level MPPT versus higher aggregated level MPPT. Now, of course, clouds, etc., would have that impact, but once you start getting bigger plants and so on, not as much. So that's the thing. But using of string inverters certainly helps in that regard as opposed to central inverters, but not significant enough to be a big deal right now. Dave had a question, is one of the important advantage of utility scale solar plants over BTM rooftop is that utility scale PV plants can provide ancillary services as well as be controlled by the ISO to improve grid stability. Yes, indeed. In fact, utility scale plants can be controlled much better, and they work as any large plants which require that level of control. Now, can rooftop BTM PV, behind the meter PV, can also be controlled by ISO? In a technical sense, yes, it can be, but practically it's very difficult to do so. It's owned by individual homeowners or individual customers, and it just gets messy in terms of the whole infrastructure of controls and who sends the control signals and how and cost and so on. So it's in a strictly technical sense, yes. Practically, no. Peter, great answer. Thank you. Okay. Any other questions? Or if you think of them another time, feel free to drop me an email or get in touch with me, and I'll be happy to support that as well. Okay.
Okay. Well, thank you so much. I checked with our group here at UT, and no questions in the room. But we really appreciate you taking the time to give this presentation. So thank you once again, and please, if you'd ever like to update us once more on the state of the industry or what you all are doing there at First Solar, we're ready to have you back.
Okay, sounds good. And thank you again for inviting me to give this talk, and thank you for your audience as well, and all your questions. And I hope it was. I know I rushed through a lot of material, but I hope it's worthwhile to get a broader picture of the way we are looking at this as well. Okay, of the industry.
Great.
Thank you, everybody.
Yeah, absolutely. And just for those of you in the room, just as a reminder, we will have a recording of this up. So if you'd like to go through the slides again and hear what he had to say, or share it with your colleagues, then we'll have this posted within the next day or two, and there'll be a link on our Twitter, Facebook, our webpage, etc. So thank you again, Mahesh, and thanks everyone for attending.
And I sent you the presentation so you can pass that along too.
Oh, great. And then so we will also share the slides as well. So thanks for that, and we hope to have you all back again.